I think about everyone is here, so I guess we can get started. Thank you guys for showing up to algorithmic problem solving. Today is the advanced lecture for the graphs portion of the class. So last time we covered disjoint set union, and within that we looked at path compression as well as merge by size. We looked at Kruskal's algorithm for minimum span, and then we also looked at the Kruskal reconstruction trees. We'll be extending on what we did last lecture, as well as we would also look at a few extra problems. So we'll be looking at a few extra applications for the merge by size, which is in general just called small to large merging. We'll also look at extending the disjoint set union to allow for rollbacks. We will look at the application for that for the persistent union find, which I find particularly interesting. And then we'll also be introducing articulation points. So first we'll look into small to large merging. So here's a particular application for this idea. So in this, you're just given a tree and you're just tasked with finding the number of unique colors for each tree. And for example, you would say that like the number of unique colors for the subtree that starts with 7 would just be 2 because red and blue are the only unique colors in that particular example. And I guess one naive solution that you can think of is just storing all the colors you've seen like within that tree and then doing a depth first search. I guess, does anyone have an idea what the time complexity of this algorithm might be? Well, it turns out to be O of n squared, and it's pretty simple. It's just because like you have n subtrees, and then within the construction, you have to merge two like lists that could be of size n. So that means that you have to do n work n times. So that's O of n squared. And I would say one idea that we could look at for improving the runtime would be to reduce the amount of work we do for the list. And we could either do this by reducing the number of times you have to merge to a list or reduce the size of the list. I would conjecture that reducing the size of the list that we're merging might be the best. And that turns out to actually be the case. It turns out that if you use small to large merging, where you merge conditioned on the set of the size of the list that you're merging, is actually pretty optimal for getting to n log n. And we can do the analysis for why this is the case. So you can analyze this instead of looking at the cost for each list insertion. You can instead think of each move on a color by color basis and think about how many moves each color has to do. So if you choose to merge a smaller list into a larger list, intuitively it makes sense that this takes less work because instead of doing the amount of time it would take for like the larger list, which might be like let's say m, which is larger than n, it might be like O of n, which is in this case the size of a smaller list, which is smaller than m. But in actuality, it's actually better than this because if you think about this from the perspective of the smaller list, the smaller list is joining a list that's like twice the size of the small list. And similarly for the merge by size that we saw for the disjoint set union, this means that for the colors within the smaller list, the bigger list that it joins has like double the number of unique colors at least. And since there can have at most be just n colors, which is the case where every vertex is a unique color, then that means that you can really only double the number of unique colors within the list a logarithmic number of times, which then means that each color can only move like a logarithmic number of times. Where in this case, the color isn't every instance of like red, but like the assignment that the color has like for 5, I would say. And since there are only n colors and each color has a logarithmic number of moves, then that leads to n log n runtime complexity. And we can just do a quick live coding of this to show it's a really simple fix that reduces from n squared to n log n.
Yeah, so this problem here is just what we covered previously. You're given a tree with n nodes. Each node has a color, and for every node, you want to calculate the number of distinct colors in the subtree. So we can basically implement the small to large algorithm we discussed like right before this. So here we first have kind of like an input template. We get like the number of nodes in our graph. We get the initial colors, like C is the color of each node. We get our tree in adjacency list format, and then we initialize this array is basically for every node, what's like the set of all colors in its subtree. So we'll initialize it all to just itself, since itself is in the subtree. So how we'll do this is we'll run a DFS going through, and for every node, we'll kind of merge the distinct colors in the children's subtree into kind of the nodes set, because the children contain all the nodes in the subtree. So how we'll do this is we'll start by defining kind of I guess, first of all, does anyone have any questions about this problem or kind of how we're going to be approaching it?
Yeah. Just to be clear, what is it again? You guys are just trying to find all the colors in the subtree?
Yeah, all the number of distinct colors in every node subtree. So we'll do iterative DFS. We covered this last Friday, I think, because Python recursive DFS is slow. So we'll do recursive DFS. We need a stack. We'll have the node, which we start at 0, no parent, and then status 0. So this is node parent status. Then while our stack is not empty, we'll pop out the last element on the stack as the thing we want to process right now. So that's node. And now if status is 0, this means we haven't processed, so start processing children. As first, we need to mark it as processed. So the 1 marks it as processed. Then we'll iterate through all of its children. So and then we will just add the children to the stack as like unprocessed. So the other case here is if status is 1, this means we've already processed all the children, which means that we can assume that this node has the correct kind of we can assume that this node has the correct like set of distinct colors in the color set. So what we can do is we can kind of merge it with its parent. So so its parent has set and wait, first of all, we don't want to merge wait. So if it's the root, we don't want to merge it with its parent because it doesn't have a parent. So we'll first do that check. Then we want to merge sets 1 and 2 together. So if set 1 is smaller, then we'll swap them. So and then we'll merge. So now we have that set 1 is like, or the size of set 1 is greater or equal to the size of set 2. So then what we'll do is we'll merge set 2 into set 1, since set 2 is smaller. And we can do this with a very simple command, which is just set1.update set 2. This just takes everything in set 2 and plops it into set 1. So now that we have kind of set 1 contains our merged thing between the current node and its parents, we want to kind of update the parents set with this new merge set. So we'll do colors We'll just update it here. And then finally, we need to like somehow store the answer. So here, when we've already processed all of its children, this means that all the children have already kind of sent up their subtree into this current node's color set. So what we'll do is we will answer to be just the length of our colors. So then after we run iterative DFS, our answer array should contain all of our basically the number of distinct colors in our subtree, since that's what the length of the set is. So, and then if we try to run this, we need to put this before, because you also need to calculate it for the root. We just don't want to merge the root with its parent. So we need to move this before this root check. So if we run this, we get 3, 1, 2, 2. This means the root has 3 children. Node like 1 has 1 children, distinct. Sorry, the root has 3 distinct colors. Node 1 has 1 distinct color. Node 2 has 2 distinct colors, and so on. And if we look at here, that matches up with our sample output. So we'll go ahead and submit our code now. Perfect. And then hopefully we'll see that very soon. It will say accepted. So this passed very close in the time limit because this is just a pretty like beefy problem. So we had to do a lot of optimizations to make it pass. One of them is small to large merging to make our time complexity down from n squared to n log n. We also had to do iterative DFS to just speed things up by preventing like Python recursion from slowing things down. So I guess I'll pull up the, does anyone have any questions on, I guess, how this code works, especially in the DFS section? All right. So that's it for this problem, and we'll continue on to a different application.
And we're still on multi-large merging, and another application for it is the knee-rolled query problem. And the idea is just that you have a graph and you add edges to it over time, and for a number of queries you want to answer, given A and B, what was the first day that you could like take a walk between the two? So for example, here, if the query was 1 and 3, then the first day would be 2, as that's the first time when 1 and 3 are in the same connected components. Then you can see a few other examples for 4 and 3. It's the same case. They're initially in 2 different connected components, but then once that connected component was when those 2 were merged into 1, then that's when the answer resolved to 5. And same thing for here. And it just gives you an idea that maybe you would want to do a disjoint set union, since it seems like the problem in just answer changed every time where we were able to merge 2 components. So it would think it would be useful to keep track of the components. And as you see, if you run the disjoint set union algorithm, you can sort of get a data structure like this. And you could think of just at each point where you merge 2 components, you could just scan through the list of queries you received and figure out whether any of the queries were resolved at this point in time. However, since the number of queries may be large and you may make a lot of edges, this could be slow. So an idea to speed this up is to actually keep track at each like leader for the connected components, what queries that component is involved in. So for example, here everyone is just a leader for itself if you were here for like last lecture. But then as you move forward, 2 becomes the leader of the bottom connected component, and then it sees that it's involved in query A and query D, as it contains node 1 from query A and then node 2 from query D. And then this allows you to just do set merging. And once you merge two sets, you can see that you had two connected components that were involved in the query. And then you see that that was query A. And this happens exactly only when we have a query where both nodes are in the connected component. And that's pretty much just our answer. Since this happened on the second day, then we would return 2 for query A. And you can repeat this process, keeping track of when two query points meet up, and then you just record the data that happened. So here, for example, query C, the answer would be day 4. And then that continues for D and B as well, because on day 5, the connected component 4 and 5, and then the connected component for 1, 2, and 3 had nodes from both query D and B. Does that make sense? All right. So in implementation, you just split up the query into like 2 virtual half queries, and you store these in each component's leader. So initially, each node is all by itself, since we start off with 0 edges, and then as we move through the operations where we add edges, then that's when we run the disjoint set union algorithm and we merge. And then here you can see a bit more clearly of how this would occur. So you would you just have a list of queries for each, and we run into the same issue for the coloring problem, where the list of queries, even though this is better, the list of queries can still be like O of n, or just O of the number of queries in the problem for each list. However, if you do the small to large merging again, then that means like the smaller list is joining a list of size at least double. And since you can only double the number of queries up to like log of the total number of queries in your problem, this gives a log of the number of queries. So it's n log n if n was the number of queries. And does that make sense? It follows very closely with the coloring analysis. Oh yeah.
Like the 2 slides ago. So
Yep.
yeah. So the reason why we stored the queries the thing was involved with,
Mhm.
the alternative would be to just like check if the root or like the leader at each day is the same for each, but
Oh, so not, I would say not exactly. For example, query B3 isn't really the leader here. So if you were to, when you merge the 2 components together, you would have to search through like all like 4 queries, or just the 2 that weren't answered. And then you would have to like search through both trees to figure out whether like one half of the query was in one and the other half was in the other, which is just it would take a decent bit. Is that like what you're like, asking?
yeah, I'm not exactly sure. I was like, oh, for example, if we wanted to see like if query A is fulfilled, so 1 and 3, then like at each day you would check like, oh, is the leader of 1 is the same as the leader of 3?
That's also another way of doing it. That would give you a different time complexity, but you could at like each time step just check all the queries again and see if they're now connected.
So that would be quicker.
It depends on the number of edges. I think that would be like m times the number of queries times n log n, which maybe it could work better. It sort of depends on like without the n, but that's you get a different time complexity. But you can avoid all that work if you just store in the leader what queries you would have to look at. Yeah. Okay, and then this is a bit simpler, but it has interesting applications for the persistent union find algorithm. And this is just the disjoint set union, but modified to have rollbacks. And what we mean by rollbacks is just being able to undo like the last merge that you have performed. So It's pretty simple. All you have to do is just keep a move stack for like what like edges you just added, and then every time you want to like roll back, you just pop off the stack your last edge addition, and then undo the work we did in the merge. And the merge operation is like very simple. You don't really lose much information in it. It's like O1, so it's very simple to undo. Um, does anyone see why path compression might be an issue if you were to implement it with this? Well, path compression is fast, but it's only fast on average. So that means there's still the potential for long paths up where we would have to. Well, first, does everyone know what path compression is here? Since maybe not everyone went to the first lecture. We good? Okay. Yeah. So for path compression, the path could be long for any particular instance, but then over time, as you continue to like compress paths, it reduces to n log n. However, in general, it could be like worst case O of n. You can have a worst case O of n path. It just doesn't happen too often. However, when you introduce rollbacks, this is no longer the case, as you can just once you find like an O of n path, you can perform the find and compress the whole path, and then roll that back, and then repeat that over and over again, and that gives you like n squared work, which is not what we want. However, union by size is always fast, so that's why we still allow it here. And if you're just curious on how this would actually be implemented, this visual shows it. So it's a normal DSU algorithm, but then if you want to roll back the last edge you added, for example, then you could just take the last edge, which is 5 to 7, off the move stack, and then call the rollback function, and then it undoes it. And it's pretty simple, but the persistent union find can be solved using this.
Okay. First, does anyone have any questions on like rollback, or do you want me to just go ahead and implement it? And then... Okay. So here's the problem. The problem is very dense and like numbery, so I'll kind of just summarize it here. So what happens is you're given a graph. So this graph starts out with n nodes. So let's say, for example, simplicity like n is 3. So I'll have like 3 nodes. This empty graph, we'll call it g of -1. So then there's two types of kind of operations we can do. So operation type 0 is we take some graph and then we add an edge to it. For example, we can perform an operation type 0 to create a new graph with the same number of nodes, but just the extra edge added. So for example, like this, and we'll call this like G0. We can perform another operation 0 to kind of turn this graph then. So this is like the previous graph. We'll add like another edge here to make this like G of 1. We can also like, for our next operation, we can like take this graph and add an edge to that, for example. We can call this like G2. So basically what operation type 0 does is it takes some graph you have previously and you add an edge to it to form a new graph. And then operation type 1, you're given K, U, and V. You want to look at graph G of K and query if U and V are in the same component. So let's first number these. Let's say we queried like K, let's say like U and V is 1 and 3. So U is 1, V is 3, and let's say K is 1. So what we do is we look at G of 1. So this graph, and we'll check like are nodes 1 and 3 in the same component? And the answer is yes. But instead if we did like K is 0, that would mean that we look at this graph, 1 and 3 are not in the same component, so we'll return 0. And I guess as one last example, if like this were 2, then we look at this graph, 1 and 3 are in the same component, so we'll return 1. So we basically just have to support these two kinds of operations slash queries where we can either take a previous graph, form a new graph by adding a new edge, or we can ask if two nodes are connected in some like previous graph that we have. So does everyone kind of understand what this problem is asking? Yeah. Okay. So now how can we go about efficiently solving this? I think first thing that comes to mind is DSU, right? Since we want to query if two nodes are in the same component. But the thing we have to worry about is, we have a bunch of different graphs. How do we support DSU on like all of them? So if you look at kind of the structure, we can imagine we start off with like g of -1. And this has no edges. And then what happens is we'll take g of -1, let's say, and then we'll take g of -1 and add an edge to that. So that forms like g of 0. Then let's say for g of 1, we take g of 0 and add an edge to that. So then that'll form like g of 1. And then g of 2, maybe we'll take it from g of 0 again. G of 3, maybe we'll start from the empty graph. And like we can continue so on. So what this kind of forms is a tree of graphs, where you can think of each node is kind of like a different, like one of these graphs. And each edge represents like we're adding a new edge UV. So like add UV. So each of these represents like we're adding a new edge, we're adding a new edge, we're adding a new edge. So what we can do is instead of answering the queries as we go, we can kind of store them as to which grafting they correspond to. So for example, let's say we have like 3 queries in here that I'll ask for like, do U and V, are U and V in the same component for a graph like G2? Then we'll just like put them all here, and we can kind of once our DSU lands kind of at G2, we'll answer all those queries. Since our graph reflects G2. But then the question now is like, how do we go from graph to graph? Because we start at G of -1, but we kind of want to get our DSU state to every single graph so we can answer the queries there better efficiently. So going down an edge is pretty simple, since that just is adding an edge. We can just do the union function to add that edge. And now that we have a rollback function, what you can observe is that going up an edge. So let's say we're at G 4, and we want to go back up to G3. This is just equivalent to doing a rollback, since our most recent added edge is just the path from G3 to G4. So to go from a graph up to its parent, all I have to do is a rollback, which is like O1 constant time. So we can go down really fast just by doing unions, and we can also go up really fast by doing rollbacks. So this kind of lends us to a DFS style approach, where we kind of DFS through our graph states, and once we reach a graph state and our DSU is in that state, we can kind of process all of our queries that ask, like, is U and V connected in that specific graph? So if that, I guess first, are there any questions? Like, if that didn't make too much sense, hopefully the code will help it clear up a little. So we can just go ahead and begin implementing this. Yeah. So we're given like N and Q, and then basically all of our operations we have to support. So how we want to store this is we kind of also want to store this tree. So what we'll do is we'll have kind of like a child, like we'll have like children, which will be kind of like an adjacency list. And then we can have at most like Q+1 graphs, since each query can create like a new node in our tree, and there's also a node -1 to begin with. So we'll have this. We'll also need to store all the queries that like each graph has. So for example, we need to store like, oh, we want to know that like if 1 and 2 are connected for G0, if 5 and 6 are connected for G0, and so on. So you also need to store that. So we'll have like node queries, and we'll store a list for every single one of our graphs. Then we'll iterate through our through all of our queries. We'll get the input is in like TKUV. So we'll get in TKUV is then so if T is 0, this means that it's like a operation where we add like we add a new graph. So what we'll do, oh, I should make this I. So this adds new graph G of I based off of G of K. So we'll take so a child of K will create kind of like a edge down to this child. It has its to graph I, and we want to add edge U comma V here. So kind of just store that in our child array. The other case is if we want to query GK if UV connected. So we'll I'll just create this variable to store the number of like one queries we have. So we'll say like node query of like we want to query graph G of K, and we want to check if U and V are connected. And we'll say this is index n queries. And then we'll add one to the number of queries. So now that we kind of set up our kind of tree structure and like stored everything we want to know from each node, we can create our answer array just to preempt ourselves. And we have one answer for every query. And then we also need to set up a rollback DSU. So first we'll code like a normal DSU, then we'll make it support rollbacks. So the parent, set each parent to itself first, then the size initializes at 1. Then we'll implement find. So remember, we can't use path compression. So this actually simplifies it down a little bit, where if U is parent of U, we'll just return U. Otherwise, we'll just return find of parent of U. So this recursion is actually okay because it's not too much. I think it also optimizes it out a little bit, but this kind of is just our find operation without path compression. Then we also need to support union between U and V. So we'll set them to their like leaders first. Then if they're equal, we don't want to do anything. Otherwise, we want to do small to large merging. So if this means that, so we want to merge U into V. So this is our like union find, our DSU without rollbacks. So now we need to keep track of like all the changes we do and also add a rollback function to kind of like reverse them. So we'll make like a changes stack, just call it that. And every time we do a union, we kind of need to like store like what changed that time. So we'll create like a dummy thing. If nothing happened, we'll just like append none to it. So like changes append none. Otherwise, what happened is we merged we merged U into V. So let's store U so we can like kind of undo this merge of U into V. So then how our rollback function works is we'll just take the last element on our change, so like the most recent change that happened. If U is none, that means our most recent change was nothing, so we can just like quit. Otherwise, so what happened is we updated, so we know that V is parent of U. So now we just need to reverse kind of these two operations right here. So first, let's reset size of v back to what it used to be. So we'll subtract size of u from size of v. Then we'll also reset u's parent pointer because it used to be a leader. So we'll set the parent of u back to u. So this completes our like rollback function. So now we're ready to kind of perform our like DFS structure. So I don't want to recode iterative DFS because it takes a while. So I'll copy this. I don't know how this mouse works, but okay. We'll copy this into here. And we can get rid of kind of all this I don't know how this, okay, sorry. We'll get rid of all this code since this is pretty specific to the previous problem. So let me also, okay, probably would have just been, how do I highlight code here?
It's the trackpad is kind of like if you have to like go
Okay.
from that side.
Wait, sorry about that. So we'll also store an extra kind of thing in our stack. We'll also store like the edge. So the edge that like kind of like if we go here, we'll also store kind of this edge right here since we need to know that to like kind of update our DSU and also to like perform our rollback. So we'll store an edge there. First will be none because there's no edge from like the root doesn't have a parent, so there's no edge going into it. Here we'll do edge. So status is 0. We haven't processed yet. So what we'll do is first we'll like mark it as processed. Then we'll go through each of his children. So how do we store the children? We put like the index, like the new graph, then like the edge of the child. So we'll say for the child and then u and v, which is our edges, in the children of node. What we want to do is we want to kind of queue this for processing. So we'll queue child C has node the current thing, status is 0, and then our edge here now is u and uv because that's like the edge that we're adding. Okay, whatever. So now that we kind of like queue all our work, we can go in and begin like processing our children. So wait, actually, first of all, when we visit a node, we have to first kind of update our DSU. So when we go to a node for the first time, we need to kind of process an edge to turn our DSU from the parent state to the current state. So we'll say, like, if parent is not none, then what we need to do is we need to union like edge 0 to edge 1. So what this does, what this does is it like our the parent that we just gone through, we will like process that operation and add our query. So after we union this, we're now kind of in our we're like in the current state, so we can answer all of our queries. So we'll iterate through our queries, which we called node q. So for all queries of this graph, we'll sorry. So if they're in the same component, which means like find u is find v, then we'll output 1, else we'll output 0. Then we'll store this in our answer. So like ans I is this kind of answer. So now we've like answered every query for this node and we can keep going. So the last part that we have to worry about is our rollbacks. So we can now traverse down the tree, but we haven't coded up like reversing and going back up the tree. So again, if the parent is not none, which means that there is a parent to go up to, we'll just perform a rollback. So after we kind of perform all of this, we should update all of our answers correctly to reflect kind of all the queries that are for that graph. So if we run iterative DFS, then we print out like all of our answers. We should hopefully no. Okay. So something went wrong. Let's see. Wait. Wait. So, ooh. No, okay. Huh. This is not good. Yeah. Wait, the red doesn't matter.
Sure if it's relevant for this problem. You check out the child's or if it's.
We only store the children, so we only store like one way. So graph I is based off GK. We only store I is based off GK. No, it's 0 indexed. We can pull up our previous solution that we submitted, we got accepted for, and kind of walk through this. Oh, wait, no, we did do that. Wait, I think I see something fishy.
Oh, -1 instead of 0.
Where is -1?
The first node is -1 instead of 0.
You're so right. Okay. Very correct. Okay, let's try this. Okay, that worked. That's the right answer. So sorry about that. Yeah, so our root there is -1. So we should start with node -1 instead of node 0. So if we look at the sample output, oh, it is equal to this. So we'll try and submit this now. And I guess while we wait, does anyone have any questions about this code? Especially any of this like tree traversal or like the rollback?
Okay, so what is the alternative to storing the operations and like undoing them? Like what would be the alternatives to that, which I imagine is like worse?
I guess one thing we could do is like process everything in order. So okay, first we got accepted. Yay. Okay. And then one thing we could do is, for example, let's say we go through, like if we don't think about this tree structure, one way we can do it slowly is that we could just add edges and like and then like every time we want to query a node in the past, we kind of just roll back all the way there, and then we like kind of like add edges to get kind of back to where we were. But that requires like if you want to go back to the very beginning and then like come all the way back to add a new edge, then you have to like go back and forth a lot. So that's kind of why we store the queries at each node and
Oh, okay,
do
so you
this.
can do like each query in order, but
Yeah.
it could be about like
Like-
nodes that are really far apart.
Yeah, and you have to like waste a lot of time just going back and forth. Yeah. So yeah, that was a implementation of kind of like an application of rollback DSU. And finally, we'll quickly cover articulation points.
Right. Yeah, we're covering articulation points last, and pretty much what the idea of the problem is that if you have a connected graph, then you have things called articulation points, and then you also have bridges. And an articulation point is just a vertex where if you remove it from the connected graph, it becomes disconnected. And then the same thing goes for the bridge, where if you remove it, then you increase like the number of connected components from one to some larger number. And we're just tasked with returning what vertices are articulation points and what edges are bridges. And I guess intuitively, one thing you might have to think about is whether the graph is already connected. So maybe we could just do a DFS to check if the graph is actually connected. And then we could just store like what edges we used. And then in that way, we sort of like get this tree structure. And an interesting property with this, first of all, the black edges are the edges we use within the DFS, and then the red edges are the edges we didn't use, which you call them back edges. And does this like make sense? Why this would make like a tree structure? All right. So one nice property of producing this tree using depth first search is that there isn't going to be a case where a back edge like traverses just like a different branch. So for example, there would never be a red edge going like from 8 to 7 while these two branches were still here. As if that was the case, then during the depth first search, then it would have traversed from like 8 to 7, and then it would have became one really long branch. And the nice property with this is that this allows a sort of strict ordering with all the vertices within each branch. So this means we're able to define a unique depth for each node, as well as a value that we call the low, which is given the back edges that are ahead of this node, like how far back in the tree can you go? So for example, for nodes 3, which is right here, the value of low would be 1, since you're able to go to some back edge back to node 1, if that makes sense. Does that make sense? So if you want to think about removing a node and how it would make this graph disconnected, you can see that removing any node like from the tree makes a tree disconnected. So for the graph to like stay connected, there has to be a back edge that like bypasses that node. And more like, I guess more rigorously, this can be defined as any of the children being able to get behind this node, since the depth is totally ordered back towards the roots. So for example, 1 is an articulation point because both of its children here are able to are not able to reach the root behind the first node through any back edges, right? And this is sort of a if and only if condition, and this also holds for the edges as well. Since if you remove this edge, then any node below it can only connect to the rest of the graph if and only if there's a back edge that is sort of parallel to this edge, or more officially, like there's a edge where the lowest vertex it reaches in terms of depth is just the is above the current edge's lowest vertex. And to compute this, you can use targens. So it's pretty efficient, since the lowest is only is like increasing, since as you like go further down this chain, then like you can only do like strictly worst. You can sort of like take the minimum over time of the worst depth you can reach through the back edges. So through this, it's just computing the minimum across like all the depth of the edges that it can reach through a back edge for its children. Does anyone like have any questions on like how this would like why this works? All right. So yeah, it's pretty simple, and I guess that's really about it. Um, yeah, I would recommend asking questions. It's once you get it, it's pretty intuitive, but it's very easy to get something wrong here. But if we're all good, then we can end the lecture.
Do you have like an example?
Oh, yeah. What? Oh, can finish your question?
No.
Oh, yeah.
Like walk through it.
Yeah, we can just walk through it here. So for the for like calculating what the low value would be, you would say you would see here that like the only back edge connected to 3 is this red edge and it connects to node 1. So then you would store like low 1 here. And then for 2 there isn't a back edge. So like you would take like the minimum of 2 of the back edge of its children and like the depth that the back edge is connected to is, but it's just the minimum of like 1 and nothing. So then this just is 1, and then that's like 1 as well. And then for the root, you like stop looking at 1 because the back edge sort of like terminates. Um, does that make more sense? And then like conversely, that sort of like represents you being able to like go forward in the tree to reach this back edge. So like 2 is an articulation point because 3 can go to the back edge, sit node 1, and then it sees the rest of the tree. Right. Was that the last question? Are we good? If so, you could just fill out the attendance form and the raffle counting. And are we on we're doing the mini raffle? Or are we doing split one? Like right now? Right. Yeah. So I would stay for a few more minutes, and we'll do like a mini raffle, and we have a few like tiny things to give out. Some of them are actually pretty big, so you'll stay. You'll enjoy it. I promise. But yeah. Thanks for coming to today's lecture.